Supercapacitors are rated at certain operating conditions. So the operating temperature of a supercapacitor, so the optimal temperature or the working temperature, is typically very broad from -40 to +70 degrees C. However, this might vary for individual kind of supercapacitor. So the capacitance has a certain tolerance. This is the percentage deviation from the nominal capacity, and this can usually be ±20%, also depending on temperature and other working conditions. The capacity reduction, so the drop in capacity compared to the baseline at which the capacitor is rated, can be about 20%. And the mass of a capacitor, so the weight of your capacitor, can range simply from a few grams and therefore very small energy storage up to several kilograms and therefore very notable energy storage. The cell voltage is always given as a nominal cell voltage. So this is the voltage range in which you can also charge and discharge your capacitor. This is something very important because we've seen that for the charging voltage and also for the charging current, the cell voltage is an important part determining how the charging behavior and discharging behavior of your capacitor happens. So this is something which should also be paid attention to apply only voltages which are within the rating of the given capacitor. So all in all, based on these values, we can actually say that capacitors pose a versatile system which can operate at a variety of conditions and application fields due to a very wide span of temperature uses and voltages and weights, for example. Now, having a deeper look into the application of supercapacitors, I want to make a clear distinction here, which is a little bit of a repetition from what we've seen earlier. Here you see a supercapacitor rated at 65 farad, one at 10 farad, and one at 5 farad. I don't want to look so much into the trend here. What I mostly would like to point out to you is that the energy density here is about 3.9, 1.1, 2.2, so it's relatively low. The power density, however, both are given logarithmically, is significantly higher. And here is the important point I want to make. The energy density is basically the quantity of energy stored per unit of mass and per unit of volume. So this is giving you an idea about the overall stored energy. Now the power density is the energy density with respect to time. So here we are looking at how fast we can transfer electrical power per unit mass or per unit volume into this storage or out of this storage. And the higher the power density is, the higher the current to withdraw or to charge our storage device can be. So a high power density usually means that you can obtain a fast charge and a fast discharge. I don't want to focus too much on the trend here, so this is simply 3 literature examples, and usually the energy density does not correlate so strongly with the size of the supercapacitor, so please don't worry too much about this. I would just like to show you that a 65 farad device, for example, might be usable for industrial applications, for rail vehicles, or for automotives. A 10 farad supercapacitor is typically used, for example, for smart electricity meters or computer backup, and a supercapacitor with 5 farad might be used for electronic equipment. Now, how does the supercapacitor compare to a technology which you know, which might be, for example, a lithium-ion battery? And here you readily see why supercapacitors are often not used more widely. So in green here, you first of all see the energy density. So the amount of energy stored per unit mass and per unit of volume in lithium-ion batteries can range from 50 up to 260 watt-hours per kilogram. So again, significantly higher values than our supercapacitors, meaning our lithium-ion batteries can overall store much more energy than the supercapacitors. If we look at the power density of lithium-ion batteries, we have a range from 300 to 1,500. Now, the scale is a little bit distracting here because of the logarithmic nature, but you do see that our capacitor systems here, especially the 65 one for industrial applications, has like more than double the power density, so double the watt per kilogram scale of a lithium-ion battery, meaning that supercapacitors can simply charge and discharge much quicker than lithium-ion batteries. And this is actually one of the big selling points of supercapacitors. However, they always lack in energy density. So you see the amount of energy you can store in supercapacitors can be put in there and put out of there in an extraction process very quickly. However, the amount you can store in there is relatively low. Just as a side note, I want to say that lithium-ion batteries are also typically either engineered to obtain a high power density or a high energy density. In most cases, you cannot really obtain both of these. So typically, if you have a high energy density, you have a relatively low power density, and the other way around. It's hard to obtain both high values at the same time. Findings, we usually define supercapacitors due to their ability to provide large amounts of power within a limited amount of time, and due to their high power density, we define them as power storage systems rather than energy storage systems. Again, this is because they cannot store a lot of energy, but the energy they can store, they can release very quickly. This is why they are called power storage systems. Typical application areas for supercapacitors are, for example, found in providing starting energy in the transport sector, as a reliability for power supply systems, or as bridging or compensating for short-term load fluctuations in the electric grid. The market share of supercapacitors is therefore very much widespread. So we have a part in consumer electronics, in the industrial sector, but also the automotive sector, and in the electric energy in the electric energy sector, and a small portion being others. In this part of the chapter, I would now like to have a look at real-life applications of supercapacitors, where they are commonly found and where they are the clear choice when you are looking for a storage. Because in these applications I will show you, you're looking for a power storage rather than an energy storage. The first example I would like to focus on are wind turbines. The function of supercapacitors in wind turbines is that they should help the rotation of the rotor head or the blades. This is necessary to adjust to the angle of attack of the wind, or with very high wind speeds to prevent damage to the turbine. And the requirements for electric storage to serve this purpose is the adjustment requires high power, because you have very heavy blades, so you need a strong motor to turn them, and therefore you need a high power. And also you need some kind of possibility to provide energy at very remote places. And due to this adjustment taking place frequently due to changing wind directions, you need a high number of cycles. So because you don't want to replace these parts every year or every 5 years, typically you're aiming for a service life of around 15 years. And this is a typical application areas of supercapacitors, because they can easily be operated at remote places, they provide high power, and they usually can be charged and discharged very, very easily for a high number of cycles, providing they are operating at suitable conditions. Another example where they are commonly used is the transport sector. In the transport sector, they can be used to harvest energy from braking instead of dissipating it as heat energy. You have to see that a conventional brake uses friction brakes, basically. And using friction brakes, when you're braking, you're doing nothing else but converting kinetic energy into heat energy and simply dissipating that to the environment. However, you can use, specifically in electric vehicles, you can use the electric motor as a generator as well, or you can use supercapacitors in order to recuperate this energy, or this technology in general is called regenerative braking. So how this works is during braking, you use this energy to charge your supercapacitor and you release this energy again upon acceleration. After all, this yields energy savings of up to 30%. The requirements for material or storage technology serving this purpose is again very fast charging and discharging, because once you brake, you immediately want to charge your storage. It should be efficient short-term storage. You're not aiming to store energy for a day or a week or even longer here. Mostly it's about seconds to minutes. And it should be a technology which is also compatible, for example, with trains or with electric vehicles or hybrid electric vehicles. So it should be a suitable size to fit in there. And here, supercapacitors are also the technology of choice. To conclude this chapter, we should state that avoiding the conversion of electrical energy into other forms of energy has the big advantage of avoiding potentially high conversion losses. Because if I have an excess in electric energy and I first of all have to convert it, let's say, to thermal energy or to mechanical energy or chemical energy in this cross-sectoral system, we do have a lot of sources for energy loss. So using electrical energy storage is therefore, I would say, the purest form of storing electric energy, of course, because it doesn't convert it, it just stores it as it is. However, this advantage is now offset by the clear disadvantage of extremely low energy densities, which is both in terms of volume and weight very unfortunate and places exorbitantly high costs if we're thinking about utilizing supercapacitors as a large-scale energy storage system. So electrical energy storage with supercapacitors or with capacitors in general is presently only used in niche segments or for certain specialized applications, as I've shown you.